This is a fragile house of cards, and this is a robot that I built that has a LiDAR sensor. I'm about to drive this thing at full speed directly at the house of cards, and if I've done everything so far correctly, it should stop before it hits it and back up safely. All right, let's go. Last time, we explored the basics of LiDAR and how it sees the world around it in 360 degrees. But today, I want to actually build something with it. I want my XRP robot to map its surroundings, avoid obstacles, and maybe even warn me when I'm getting too close. Here's the plan. I want to control the XRP using a game controller like this. I also want to use LiDAR for object detection. And I don't know if this is possible, but I'm hoping I can get the controller to vibrate when I get too close to something. Sounds simple, right? But I've been doing this long enough to know that when I go to integrate all of these components, that I'm definitely going to run into some problems. There are a lot of unknowns. For example, how am I going to actually connect the LiDAR sensor to the XRP? Am I going to be able to use some of the extra connectors on the side, or am I going to have to solder directly to the MCU? Once I get it connected, I know that I need to talk to the LiDAR sensor using a serial UART protocol. But am I going to use hardware serial or software serial? There's a trade-off between these two options. I would prefer to use hardware serial because it's much faster and more reliable than bit banging using GPIOs. But a lot of the GPIO pins are already spoken for, so I may have to rely on software serial. Another thing I'm unsure about is how I'm going to mount the LiDAR sensor to the XRP platform. Am I going to have to design and 3D print a custom mount, or can I figure out a way to just mount it directly? Then there's the matter of the game controller. I actually tried to get this to work with the XRP when it first came out, but at the time, the MicroPython libraries didn't support this connection. So I'm going to have to figure out if that's been updated or if I need to figure out a workaround. I have a lot of questions that need answering and a lot of testing to do. So let's dive in and see if I can get this idea to work. At the very least, I might learn something. First things first, we need to plan how we're going to connect the LiDAR sensor to the XRP and get it talking. So let's figure that out. The XRP controller is running a Raspberry Pi Pico 2W, and it has 3 serial ports. The first one is just the serial port that's routed through the USB connector, and it's the one that you see when you use serial print statements in your code. If I want to find the other 2 serial ports, I need to look at the pinout diagram that I have pulled up here. I can see in the upper left-hand corner here that one of the serial ports is routed to GPIO pins 0 and 1, while the other one is a little less clear. It looks like GPIOs 4 and 5 could be one option, or GPIOs 8 and 9 could be the other option. So in order to test that, I'm going to write a quick simple Arduino sketch, and I'm going to write out to the serial ports, and then I'm going to use an oscilloscope to probe those pins to see which one it is. My Arduino sketch is going to be just 2 lines. I'm going to do serial 1.begin, and I'm going to set the baud rate to 115/200. And then in my loop, I'll just say serial 1.write, if I can spell that right, and I'll just send the hex value A5. Now when I compile this and load it onto the microcontroller, it's just going to send that A5 hex value over and over and over, and we should be able to see that on the oscilloscope. Looking at the pinout again, I see that serial 1 transmit pin is routed to GPIO 0, so let's have a look at that on the scope. And there we go, I can see serial data being sent over and over. Perfect, so now let's try the serial 2 port. I'm gonna load that code onto the microcontroller, and from the pinout diagram, I can see that the transmit pin is either GPIO pin 4 or GPIO pin 8. And I'm gonna probe pin 4, and that just looks like it's a constant 3.3. So let's probe pin 8, and there we have it. That's our data being transmitted over and over. So that tells me that the serial 2 port is connected to pins 8 and 9. Fortunately for us, both of those pins are broken out in 2 different places on this XRP controller. I can get access to those pins either on the large expansion headers, or I can get them on the Servo 2 and Servo 4 connector. The nice thing about the Servo connectors is that they also provide ground and 5 volts, so I think I'm going to go ahead and use those. I need to create a wiring harness that will connect the LiDAR sensor and the XRP controller. So let's connect these 2 devices, and I'll explain how the data packets flow from the LiDAR sensor to the XRP controller. As the LiDAR sensor is spinning around, it's sending packets of measurement data. Each packet has 5 bytes in it. Within those 5 bytes, there are a few different things that are encoded. All of this information is found in the RP LiDAR datasheet. The first byte contains the quality of the measurement, as well as a start bit and a complement of a start bit. The second byte contains part of the angle measurement, as well as one bit that is called the check bit, and it's always set to 1. The third byte contains the rest of the angle, and then when you combine the fourth and the fifth bytes together, that gives you the distance. I need to find a way to parse all of this measurement data while keeping everything as nice synchronized packets. I'm gonna be honest, it took me a long time to write the code to parse these data packets. As these bytes come streaming in over the serial buffer, I had to check each one individually as well as the next one to make sure that the state of the start bit, the complement of the start bit, and the check bit were all the right state, and that would tell me if I had a valid starting byte of my measurement packet. Here's what that looks like in the code. I've got a while serial 2 is available, and I want to make sure that I have at least 5 bytes in the serial buffer. Using a serial peek here is actually kind of a cool technique because it doesn't actually read it out of the serial buffer, it just checks the contents, and in this case I needed to know what the contents were of the next byte without taking it out of the buffer. And then I use an if statement to make sure that the start bit and the not start bit are opposite of each other, and that the check bit is set to 1. If all of those conditions are met, I know that this is a valid starting byte. From there, I just read in the next 4 bytes, and then I can parse that data into distance and angle. If I want, I could just print all of that information all the time, but it gets really overwhelming. So I used an if statement to filter out all the different angles except for the ones that are closest to 0. That way I can validate this code using a known distance at a known angle. Let's load this code on there and see if it works. I've got a metric measuring tape and I've got a white lid for a good reflective surface. Let's set the measuring tape right at the center of the spinning sensor. And then I'm gonna put the lid right at 600 millimeters, and we'll see what the serial data says. Okay, it says I'm at 603 millimeters, so that's pretty darn close. I think that's pretty accurate for this sensor. The LiDAR is finally connected and streaming clean data to the XRP. I can see objects around the robot in real time. So far, so good. But what good is a robot that can't move around? So that brings me to the point of the project that I'm actually really excited about and also a little bit nervous because I don't know what I'm doing. I need to be able to control the robot using this gaming controller. From what I understand, it is possible to control the XRP using a gaming controller, but you have to connect the controller to a computer and then the computer talks to the XRP, and honestly, I'm not a fan of that. I want everything to run on the robot itself, no computer riding shotgun. There is a library called BluePad32 that works amazingly well with gaming controllers, but it's really designed for ESP32 based microcontrollers, and the XRP is running a Raspberry Pi Pico 2W. The documentation does suggest that I can get it to work with the Raspberry Pi Pico 2W, but it gets a little bit messy. So here's what I'm thinking. Why don't I just use an ESP32 microcontroller running that library, and it will take input from the gaming controller and then send simple speed commands to the XRP over a serial UART protocol. This should work in theory, but I have no idea if these parts are all going to play nicely together. Let's load BluePad32 onto this Xiao ESP32 and see if it'll connect with the gaming controller. I'm going to turn on this gaming controller and put it into Bluetooth pairing mode, and let's see if we can get this thing connected. Failed to set device information. Let's see if we can reset this. There we go. And I can see all the data come up on the screen. Let's move the left joystick to see if those values change. That's so cool. And the right joystick, brake, throttle. That is so cool. So now all I have to do is to write some more code that will run on the ESP32 and then send the speed commands over to the XRP. And of course, this is going to require another wiring harness to connect the two together. If you can't already tell by the smile on my face, it means that I finally got this thing working. I can drive this thing around and it collects LiDAR data all by itself. But I'm not quite ready to show you it working, you'll just have to take my word for it. Okay, fine, I'll give you a small sneak peek. But I'm gonna disconnect the LiDAR sensor because I don't want it flying off and breaking. Here we go. This thing is quick. But remember, the final test for this whole project is for this thing to drive around and avoid obstacles using the data from the LiDAR sensor. And I can't be driving this thing around like crazy without this thing fully mounted and secured to the robot. So let's go ahead and design a 3D printed mount and get that installed. That snap means that this robot is officially finished. The LiDAR is sensing obstacles, the ESP is talking to the gaming controller, and the XRP is responding to my commands. Now it's time for the real test. We're gonna start easy, but eventually we're gonna work our way up to more and more difficult objects. First up is a nice big DigiKey box. This robot should have no problem driving around and detecting this box. I'm gonna go straight for the box, and when it gets there, it's supposed to stop. Did you see that? It backed up and the controller vibrated. All right, I'm gonna try really hard now to hit this box. It won't let me drive into the box. It's doing too good of a job. Now let's move on to something a little more difficult. This is gonna be a little bit harder for the LiDAR sensor to see. It's the DigiKey coffee cup. All right, let's see how it does. We'll back up, go right at it. Oh, if I can drive straight. Nope. No chance, it's not even gonna hit it. There's no chance that coffee's gonna get spilled. Oh crap. I guess I should have started by saying, don't try this at home. Now, it's time to raise the stakes. We're gonna build a house of cards. I've actually never done this before. I don't even know, how do you even do it? Should I Google it? How to make a house of cards. All right, we got this. No, don't you dare. Don't you dare. You stay there. Oh my gosh, this is way harder than it looks. No! I didn't think building a house of cards was going to be this difficult. I can't even get one layer done. What if I use one of these solder mats? I have been at it for like 30 minutes now, trying to build just 1 or 2 layers. I'm not even, dang it! I know this isn't that impressive. It's only 2 stories high, but it took me probably 45 minutes or an hour to get this far. No! I think I may have to come up with a different plan. Look, I'm not proud of it, but I had to use a few dabs of hot glue to get this house of cards built. To be honest, I'd rather get credit for being able to build a robot that can use LiDAR to avoid obstacles than to get credit for being able to build a house of cards. Rest assured, I didn't build a solid fortress that can withstand a hurricane. This thing is still pretty fragile. All right, here's the moment of truth. Full throttle. It did bump it, but it did back up. It worked! That is so cool! And the controller vibrates in my hand, letting me know that I almost bumped into something. I basically just gave my robot a sense of self-preservation. Now that we've got the high-stakes stuff out of the way, let's put this thing on the ground and just have some fun driving it around where it has a lot more room to roam around. Over the last couple of weeks, we went from a bare robot to a robot that has a spinning laser on it that can detect the world around it and avoid obstacles. This project was way harder than I expected, but also way more fun. If you want to get an XRP robot and build one of these for yourself, I'll have all of the design files available on maker.io. If you haven't seen it already, go check out the video where I build 3 different claw attachments for the XRP and I deliver hazardous material to a disposal site. That's it for this video. My name is Zach and I'm the Bite-Sized Engineer. I'll see you next time.